Hi, students. As a second part of our first lecture on using panel data, I will now be covering a second method very related to fixed effects, which is called difference in difference. So just a quick overview. In the first lecture of this course, we talked about two wrong counterfactuals. Remember, counterfactual is what would have happened in absence of the program, the what if. And you can do a before and after comparison, but that does not account for the time trends that might have taken place in absence of the program. Or you could compare participants versus no participants, but that could be selection bias. Those who participate might have very different characteristics compared to those who do not participate. But sometimes two wrongs do in fact make a right in this context, where difference in difference can combine these two flawed approaches of comparing participants and non-participants and before and after. And what it really does is it compares the trend, the change over time in the treated group with the change over time in the control group. And so now here, the key identifying assumption. So with identifying, you can always just replace the word causal in it. That's what we really mean here with identifying. The key assumption to reach a causal unbiased conclusion is that the treated group would have had the same trend as the control group if it did not receive the treatment. The same idea as counterfactual, but now it's not a counterfactual outcome, it's a counterfactual trend. And that's a weaker assumption because these control and treatment groups don't have to be exactly the same. It's just that the trend would have been the same. And so let's go through an early example, because this is a very long history that in many ways predates statistics. And the canonical example was to understand the cause of cholera. And so this in any densely populated urban settings in the 19th century, there was just a high degree of defecation and not very good sanitation. People believed that cholera was spread through miasma, bad air. So they were partly right by believing that this has something to do with the horrible smell, but it's not the smell itself. Actually, it's what's inside of the water. But in any case, that was a prevailing belief. So as long as you just get the smell out of it, you can just dump everything into the Thames River, you'll be fine. And so there were two enormous cholera outbreaks in 1849 and 1854. And so many people would actually say that the true king of difference in difference is John Snow himself. This is his actual name. This is a great conversation starter in parties if you meet somebody in global health or in epidemiology, because we share a common hero who is John Snow. So he actually believed that cholera was spread through the contaminated water itself. And he's perhaps the first statistician, although he didn't do actual inference looking at standard errors, but the first statistician to use this difference in difference methodology. And so the idea was just that there were two different providers of water in London. They were called Lambeth and Southwark. So this map just shows the green was the one provider and the red the other provider. Both of them got the water from the Thames, and the Thames was just a disgusting, dirty place to get your water from, because all the defecation was just pushed straight into that water, and then people drank that water again. And so the natural experiment, and you'll see often this word used in when we talk about our methods, especially with difference in difference, because it's natural experiment in the sense that this is created by the world. The researchers themselves did not create this perfect randomized controlled trial, artificial experiment, but it happened in nature itself, and we can just observe it and then unpack the trend. So this natural experiment was when Lambeth, prior to the outbreak of the second cholera epidemic, they moved their water intake upriver. So this means that the water that they gave to the London inhabitants did not come from the disgusting water that already received all the rubbish from the London city dwellers, but it got clean water from upriver, right? And so what Snow did is he went around all of London, especially focused on areas where there's, I think, potentially every single household, and he looked at what the source of enrollment was. Did they get their water from Lambeth or from Southwark? And then he looked at the death rates, and he looked at the death rates in 1949, the first cholera outbreak, and 1954, the second cholera outbreak, when Lambeth actually had now moved upstream. And as you can see here, and Southwark, which would be our control group in many ways, there was a slight increase, in fact, in mortality rates, in 12 increase per 10,000 households, but there was a substantial reduction in Lambeth of -66. And so we'll get back to these numbers in a moment, but it's very clear to demonstrate here that the status quo that continued as normal. Southwark had an increase in mortality rates, but when Lambeth made use of clean water upstream from London, this mortality rates substantially decreased. And this is pivotal, at least we would say, in the kind of progress in understanding of the causal foundation of spreading of disease. Right, so let's go through another example that I made up, a nice visual example, before we go to the econometrics itself. And so what we're going to look at, this is actually a study that took place in India, but we're going to simplify it a little bit. And just as an intervention that gives bicycles for girls. And it's actually incredibly important to reduce the transport cost to basically, especially for girls who have challenges with walking to school, especially if they reach the age of menarche and they're kind of under threat and it's more dangerous for them. So reducing this transportation costs developing countries for girls is actually really important, and bicycles is one way of doing it. And in this case, we're going to have a situation, for example, that a program introduces bicycles, but very importantly, it only gives the bicycles for girls. So we do not have a randomized controlled trial, but we have a treated group, the girls that receive the bicycle, and the control group, the boys, who never receive any bicycles. And we want to know what's the impact of receiving bicycles on learning for girls. And so let's do just some notation quickly to keep us on track. We do this Y overscore T0 to indicate the mean outcome in the treatment group before the introduction of the program. So very careful now, we're not talking here about potential outcomes, we're just talking about the average outcomes. The bottom here, 0 or 1, refers to pre versus post, and the top value there, T, refers to the treated group. That line that goes over the Y, whenever you see a line like that, that just means it's the average, right? So this is the average outcome in the treated group, pre-intervention and post-intervention. So in the pre-intervention, the girls, the treated group, have not yet received bicycles, but in the post-intervention, this is a period when the girls had already received bicycles. Similarly, we can define the same way for the control group. Now, the control group just refers to boys, and so the C superscript refers to control group, but the subscript 0 and 1 refer to the pre and post periods, respectively. So very important for difference and difference, you always need both the treatment and the control data on both the treatment and the control group before the program started. So you have a pre-intervention period and a post-intervention period. And now what you can very easily calculate is just the trends over time, the change before and after the program was implemented targeting girls. And that's just the average outcome for the treated group, that's girls in the post versus the pre-period, and the average for boys in the post versus the pre-period. Very easy, right? We just have 4 values here. 4 values is the 4 averages for the 2 different groups in 2 different periods in time. That's all you need for difference and difference estimates. Right, and so visually, I think it's really nice. What's beautiful about difference in difference, and you'll see later with more papers, you can tell the whole story visually, and it can be incredibly compelling just to have the right figure to really get your point across. And so here in our very stylized example, let's just assume that we had in this pre-period, we have this blue line, because we're looking at this trend, referring to the treatment group, and they're the goals. And so let's just say learning levels was 0.1, whatever that means. We're just making up some values for girls, and it was 0.2 for boys. So, okay, so boys are doing slightly better than the girls. And let's just say we measured learning again afterwards, and then it was 0.4 for girls and 0.3 for boys. So there was improvement over time, but a much larger improvement for the girls. So if you want to calculate the trend over time in the treated group, it's just clearly 0.4 minus 0.1, right? So there was an improvement for girls of 0.3. Similarly, there was an improvement for boys. The boys refer to the control group of 0.1. You just subtract 0.2 from 0.3, right? And so now we have this thing where the difference in difference estimate, this is where these two differences in come, is you look at the difference between post and pre for the treated group, and you look at the difference between post and pre in the control group, and you subtract those two from each other. That's where you get the second difference from. First difference is looking at the change over time, the trends, and the second difference is subtracting these two trends from each other. And so you basically just have 0.3 minus 0.1, which is 0.2. And so in here, in this case, the treatment effect of this program is improving learning for girls by 0.2. It just has this 0.2 standard deviations. There are actually two different ways of doing this difference in difference, and you get the same answer. And you can either look at the trends over time, right? The change in the treatment group subtracted by the change in the control group, or you can look at the difference between treatment and control in the post period and subtract from that the difference in the pre-period. And in this case, you have comparing in the post period, the treatment versus control. The girls are doing slightly higher, better than boys, 0.3, 0.4 minus 0.3 is just 0.1. But in the pre-period, the girls were actually doing worse, right? So the girls' performance, the treatment group in the pre-period is 0.1 minus 0.2 is minus 0.1. So this is the 0.1 minus 0.1, which is 0.2. But you only have to remember the one that there is just trends over time, and you compare the trends. And now this is the crux of the matter, and we'll be getting into way more complicated difference in difference models in the next week's lecture. But the crux of the matter is the key assumption here is what we call the parallel trends assumption. So why are we saying parallel trends? We just, and it's also called sometimes common trends, we are implicitly assuming when we are estimating this treatment effect of 0.2, is we're saying that the treatment group, of course, we can't observe the treatment group if they did not receive the treatment. We don't know what the learning for girls in this case would have been if they didn't receive the bicycles. But we're assuming that their trend is exactly the same trend as the trend that the boys faced, right? So our counterfactual trend in learning for girls, which is the treatment group, is just an increase of 0.1. Because that is what happened with boys. There was an increase of 0.1. And so really, of course, this line doesn't exist. This dotted line, we don't know what the counterfactual trend is, but we're just assuming that this change would have been the same and the change you observe for the boys. What's great is you don't require there to be both the treatment and the control to have the same values in the pre-period. They don't both have to, boys and girls in this case, don't have to have exactly the same performance academically, but you just have to assume that the changes over time would have been the same absence of the treatment. And so in this case, you subtract 0.2 from 0.4. So 0.4 minus 0.2, which is, again, 0.2. And it's called parallel trends, because if you draw this gray line across there, this gray line is parallel with this dotted blue line. Great. And so let's just quickly revert back to this cholera case that the king of diff and diff, John Snow, discovered for us. And in this case, you have the treated group. The trend in the treatment group, it increases from 135 to 147. This is the number of deaths per 10,000. And so, sorry, that's the control group, my bad. So the treatment group, because here in this case, the treatment is actually clean water, right? The treatment is those individuals who were served by the water source that actually moved upstream. So the treatment group went from having 85 to 19. So there was a reduction, right, of 85 minus 19. There was a reduction of 66. At the same time, the control group, that trend, is a slight increase, right, from 135 to 147. It's 12. Right. So what do we have here? This difference in difference estimate is this trend in the treated group is minus 66, right? And you subtract from that the trend in the control group, which is 12, and you get minus 78. That's a mistake. It's not 88. You get minus 78. Right. So there's reduction. But the reduction is actually larger than the 66 that we see just from the pre and the post observation for those who were exposed to this water plant that provided clean water in the post period. It's actually more, the treatment effect is actually more than minus 66, because actually the control group saw an increase in mortality rate. So the counterfactual is that there actually would have been an increase. The counterfactual here is that there would have been an increase in the treated group from 85 to 97 if they did not move their water source upstream. Great. So those are two visual examples of difference in difference, comparing the changes in the treatment group with the changes in the control. And I want to show you how to do this in a regression framework. And you will see that you are actually very familiar with this because it's just a bunch of binary variables, treatment, control, pre-post. And so you've done all of this before, actually. Right, so now we have a situation where we let treat indicate allocation to treatment. Treat equals 1 if you're in the treatment group. If you're girls who received bicycles, for example, and post refers to, so post is equal to 1 if you're in the post period versus the pre-period. So this is panel data. Remember when we looked at fix of fix, for each observation now we have two, for each individual we have two observations, right? For each individual we have the outcome in the pre-period and the outcome in the post-period, which is why this Y is subscript by I and T. So we have this additional subscript R, and the reason for this is that we might have this treatment that actually varies at a, say, regional level. Let's say this is a states that implement minimum wage increases, right? So you have individuals living in a state subscript R where a treatment took place in a specific time period, because you might have a situation where the treatment is at a much higher level aggregation than the individuals themselves. And this is why we provide treat with the subscript R, indicating the region where the treatment took place. Right? And in our case for giving bicycles to girls or boys, this R referred to kind of just being in a category of boys versus the gender, right? This R would just refer to the gender. But if we look at some areas being exposed to treatment and the other ones not, this R referred to the region where the treatment took place. And now you guys will see what's going to happen now is we can unpack and extract the difference in difference estimate by just comparing these averages. And we know how these coefficient estimates relate to the averages in treatment versus control and the pre versus post. And so we know actually that beta 0 is actually the mean in the control. Beta 1 is the difference between treatment and control in the pre-period. Beta 2 here is the change over time when treat equals 0. So the change in over time for the control group. And beta 3 is our difference in difference estimate. So let's go through that very slowly. So it's very clear to you why beta 3 is our treatment effect of interest. And so let's just go through this grid. We also did heterogeneous treatment effects last week with the same kind of grid. We indicate y superscript c subscript 0 as the mean in the control group in the pre-period. And remember, when we can think about this in expectation functions, right? So expectation function is really the population mean if you have everybody sampled, not just a random subset. Think about it also as the average if you have an infinite population. So the expected group when treat equals 0 and post equals 0 is basically just the population mean when treat equals 0 and post equals 0. And that's the expected function of, so YIRT, of course, is this whole equation plus the epsilon term. The expected value of the epsilon term just falls away and is 0 because everything is well specified and it's constructed in a way that on average the epsilon is equal to 0. So what do we have left here? We have beta 0 plus beta 1 times 1, right? Because so times 0 because we're in the control group, plus beta 2 times 0 because we're in the pre-intervention period, plus beta 3 times 0. So when we look at the average in the pre-intervention period for the control group, because both treat and post are equal to 0, the only thing that's remaining is beta 0, and beta 0 is the mean in the control in the pre-period. And so let's move one on. Let's try and calculate the mean in the treated group in the pre-period. Now, of course, this is expected value when treat equals 1. It's a treated group and post equals 0. And now you have beta 0 plus beta 1 times 1 because we have this treat equal to 1, but we have post equals to 0 and we have treat times post equal to 0. So that average in the pre-intervention period in the treated group is beta 0 plus beta 1. So what does that mean? That means, of course, that beta 1 reflects the difference between the average in the treated group and the average in the control group in the pre-intervention period, right? Now, let's fill out this grid and get the mean values for every single one of these 4 cells. If we want to calculate the control mean in the post-intervention period, right? This is expected value of y when treat equals 0 and post equals 1. This is just, I should have expectation function there, but it's just beta 0 plus beta 1 times 0 plus beta 2 times post, which is now 1, plus beta 3 times post, and that's just 0 again. And so we have that the control mean in the post period is beta 0 plus beta 2. Right, and what does that mean? Of course, that means that the trend in the control group is beta 0 plus beta 2, the mean at post-intervention, subtracted by the mean in the pre-intervention, which is just beta 2. All right, beta 2 is the change over time in the treatment group. And as we go along now to the fourth and final cell that we'll be looking at, which is now the average outcome in the treated group in the post-intervention period. Right, now treat is equal to 1 and post is equal to 1. So now if we have our same regression, which is just beta 0 plus beta 1 times treat is now equal to 1, beta 2 times post is equal to 1, beta 3 times treat times post, that's also equal to 1. So all of those terms actually stick. And we actually have a situation here where the treated mean outcome in the post-treated period for the treated group is just beta 0 plus beta 1 plus beta 2 plus beta 3. That was a mistake. There's no beta 4. Beta 0 plus beta 1 plus beta 2 plus beta 3. Great. And now we can also calculate the trend in the treated group, right? The trend in the treatment group is you just subtract the pre from the post period for the treated group, right? You just look at the average for this treated group, the average in the post period and the average in the pre period, subtract those two from each other. We know that the average for the treated group in the post period is just beta 0 plus beta 1 plus beta 2 plus beta 3. It's all the coefficients. And we know that in the pre period, it's just beta 1 plus beta 1. You subtract those from each other, you get beta 2 plus beta 3, right? Beta 2 plus beta 3 is the change in the treated group over time between the pre and the post period. And now you have your difference in difference estimate, right? Difference in difference is the trend in the treated group subtracted by the trend in the control group. It's beta 2 plus beta 3 minus beta 2, and it is beta 3. Magic. Right, so this is the third one, this interaction term between treat and post. Remember, this is here, the interaction term between treat and post. The coefficient on that one is the actual difference in difference estimate of the causal impact of the treatment. Beta 1 is just the difference between the treatment and the control when post equals 0, meaning in the difference between treat and control in the pre-period, and post is just the trend over time when treat equals 0, or the change over time. Great. So that's it. It'll take some time for you to familiarize yourself with this. This is exactly the same we did with the heterogeneous treatment effects, right? The only difference now is that this is actually heterogeneity in the treatment in the pre versus post period. And so just to summarize, difference in difference is a very powerful way to distill and parse out causal effects when you have panel data. But what's very importantly is you need some kind of treatment or program or something that occurred, and you need data on both observations that were exposed to the treatment and those that were not. And in addition to that, you need data on those same individuals before and after the treatment took place. And the identification, the causal inference, comes from the difference in the trends over time between the treated and the control group. The key assumption here is called the parallel trends or common trends assumption. And it's that the treated unit would have had the same trend as a control if they were not exposed to the program. One can never prove this assumption, but we can find very strong supportive evidence to make it a believable assumption. And we'll get into that a lot during the in-person lectures and also next week's lectures. Thank you very much. I'll see you all on Monday for an in-person lecture.